Welcome, ladies and gentlemen. So today we are going to start our next section of ecology, and we're really going to dive into sort of population ecology. So when we talk about populations and their dynamics, first off, we need to make sure that we are all on the same page when we define what a population is. So a population is all the individuals of a species that currently live together in a given area. So they are all lions living in a savanna in the middle of Africa in 2021 would be an example of a population, as opposed to a community where now we're talking about multiple species. So we're sort of diving down to a more specific level of organization from where we were last time when we were talking about those community dynamics and predator-prey interactions and symbiotic relationships and things like that that were occurring between individuals, between different species. Now we're going to focus on a single type of organism. So when we talk about population dynamics, a lot of this is based on statistical studies of those populations, something we talk about as the demographics, or the demography of a given population. That's often, you probably have maybe come across that term in terms of human demographics, but we can certainly apply those same principles to any living organism, any living population. And we use those demographics in ecology in particular to make predictions about how that population is changing over time. And often that may be that we are driving looking at different environmental conditions. Maybe it's a matter of a question of sustainability practices, um, or we're looking at evolutionary processes that are occurring and looking at how those populations have changed over time. So when we look at that those demographics from an ecological standpoint, we tend to focus on three big key features of populations. And then we could get into some more detailed discussions depending on the questions that we're asking. But those big three key features are the size of the population, the density of the population, and then how are the individuals within that population dispersed? Are they sort of clumped together? Do they sort of space themselves out uniformly, or does it kind of seem to just be random where they are found from one individual in their population to the next? So today we're going to focus just on that idea of size. So simply the number of individuals in a given area for that population. In our picture here, there happens to be two swans. Um, so we are directly trying to determine the overall size of this population, how many individuals are living there. One of the interesting things we can do with that population size is sort of take that population and divvy it out based on this idea of an age structure and age pyramids. So age structure is simply looking at the population and the proportions of individuals within that population at different age groups. Well, why do we care? Well, this is going to have an increase, or I should say, an impact on how your population is going to grow over time. Where do you have the largest portion of your populations? Are they at the bottom of the pyramid? So the youngest age bracket? Are they mostly children? Do you have a lot of individuals at the reproductive age? Or do you have a lot of people who are sort of post-reproductive, sort of elderly, if you will? And this is going to give us some ideas about the growth rate. So how many individuals are being born, or this term called natality, your birth rate, as opposed to how many individuals are currently dying in your population, or what's your mortality rate. So when we look at the overall sort of natural increase of population, if we put this into a relatively simplistic math equation here, that natural rate of increase is what we determine as a variable called R. And we look at the birth rate, or B, minus your death rate, so your natality rate minus your mortality rate, how many are being born minus how many are being how many are dying off, so B minus D equals R. And clearly, if your birth rate is higher than your death rate, then your rate of increase would be positive and your population is growing, it's getting bigger. If your R value is negative, then that means that your birth rate is lower than your death rate. So the death rate is higher. More individuals are dying in that population than are being born, and so your population is shrinking. If you end up with 0, then you are not growing or shrinking based on those available pieces of information. So here's just sort of a really simplistic sort of data table of what this might look like. So we can divvy it out by time units, talk about birth versus death rates in a year, a month, a day. We can break it all the way down to the second, depending on what sort of organisms we're talking about and what's important to us, so that we look at those natural rates of increase. So in this case, this population has 4.1 individuals being born every second, 1.8 dying, and so the natural increase is a positive 2.3. So we are, in fact, growing as a population in this particular example. So when we plot these on an age pyramid, it's going to look something like this. So this particular pyramid is for a developing country, right? So overarchingly, developing countries tend to have a much larger population size, if you will, in that sort of that pre-reproductive age. So younger children, teenagers just before puberty. You have your reproductive individuals here in the middle, and then your elderly here at the top, which make up the smallest portion of the population. Um, and so you've got quite a few children being born to every family, which is why that age structure at the bottom can be so much bigger than those at the reproductive age. So they are producing multiple children per family, per mating. And then they have a relatively short-ish lifespan. You can see that they quickly drop off around 50, 60, and you don't have a lot of individuals at that high end. And there's a lot of reasons that this could be occurring. If we're talking about humans, as this one happens to be looking at, we could talk about access to clean water, to medical care and medical supplies, to um, other diseases that might be in play in that particular country. Access to education can impact life expectancy. So all of that can play into why you would see this sort of pyramid for a developing country. In this case, we also are taking into consideration males versus females, and that can also play a role and be a good piece of information to include in such pyramids when we're looking at natural rates of increase in populations, because females are the ones who are responsible for carrying the children and bearing those children. And so what does that end up doing in terms of the ability for the population to increase, where males are kind of deliver the sperm and kind of move on and can continue to produce offspring even while that female is carrying the offspring from the previous mating event. This looks a little bit different, right? So here now I'm looking at more of a developed country, something maybe like the US or some of the countries in Europe, right? Where you get a much more sort of almost square-esque structure. Not nearly as many children, right, per family, so a smaller portion of the population here, a little bit more stagnant here in the middle, and you don't have a huge drop off at the top end either until you really get to the tippy top, where you're sort of just kind of hitting your natural life expectancy as your body sort of breaks down and kind of runs out. So clearly differences in their environment, their health status, and their ability to either choose to have children or not. So perhaps access to prenatal care, family planning, that kind of thing, also may be playing a role in why you see these sorts of structures in more of a developed country as opposed to this more traditional pyramid structure in a developing country. And so here's just a sort of overall comparison, right? So a rapidly growing country is going to look something like this. Places like Kenya, uh, again, more of those developing countries. You've got sort of that slow growth here. This is something like the US, where it's much more of a almost stagnant pyramid in the sense that it's kind of very much up and down here at the bottom and not super heavy at the top and relatively even at the bottom. And then you can look at places like Italy where they're actually shrinking, at least based on this data. And I'm pretty sure this has gotten even more dramatic over time, where you have most of your population here in sort of that reproductive or post-reproductive age, pretty high up at the top, and they don't have a whole lot of children. So we may be having family sizes of, on average, maybe you're talking 5, 6 children over here per family. Here we're maybe talking 2 to 4, and here maybe you're only talking a single child per family. And so your population is going to end up shrinking or certainly not growing much at all because they're not having as many children for the individuals who are here at that reproductive age. So again, it allows you an ability to make some predictions about what's going to continue happening in that population. So when I look at something like France, well, do you think this is growing, shrinking, or staying about the same? As opposed to India, the growing, shrinking, or more or less staying stagnant?